Hi students, welcome to YourPedia. In the previous sessions, we already discussed about the detailed subject-wise analysis for your electrical engineering. Now, in this session, let us solve some questions in the power electronics subject. Okay, so what are the previous questions which were asked in the TSPSC, one of the TSPSC exam? So what are the questions which were asked in power electronics and how difficulty level, what is the difficulty level we can analyze by these questions and how we need to prepare for each and every question solving. There are different ways of techniques will be there, multiple techniques will be there to solve any problem. So at right time you need to choose the right technique to solve the problems, because in suppose if you take some options will be there for each and every question, you will have 4 options. There might be different techniques like option elimination technique will be there. So you know one answer, so you need to eliminate by using that answer you need to eliminate at least 1 or 2 options, so you will get a better probability to get the answer, means to get the correct marks for your exam. Yes or not? So like that we'll discuss those techniques in this session itself, so that how you need to apply different kinds of techniques to solve each and every questions, not only for power electronics subject, you can apply those techniques for your different subjects also. Not only for power electronics, you can apply different subjects also, until unless you have a basic idea or you have a good idea about the power any subject, whatever that subject. Let me take power electronics. If you have a basic idea about the power electronics, then you can use whatever the techniques what I'll taught now. So you can take those things into mind and you can apply similar kind of techniques for different subjects, until unless you know the detailed subject wise which one concepts. Okay, now let's move to the first slide. If you take the first slide, this is the usual weightage, which will be subject wise weightage in terms of percentages. If you take the first, which subject we are discussing now? We are discussing about the power electronics and drives, which consists of 16.7% weightage, or in terms of question numbers, if you take it is around 25 questions, or 50 marks weightage we have. This subject is having 50 marks weightage. So if you have a 50 marks weightage for this subject, it will play a crucial role in your selection. Yes or not? So this subject will play a crucial role in the selection because you have a huge amount of marks for this subject. Now let's move to the syllabus discussion. If we take the syllabus discussion, this entire power electronics is divided into 5 more micro modules, we can say. So this micro module, we call this as a first chapter or a micro module. So this micro module we call it as a which one? This topic we called it as a power semiconductor devices. So whatever the devices which will be used in power electronic circuit, all those devices comes in this topic or in this module. So in this module, what are the different types of materials will be there, and different types of semiconducting materials, and different types of devices and how they are constructing, what are the different characteristics of those devices. All those things will come into picture in this module. Now, and the second module what we are going to discuss in power electronics is, that is phase control rectifiers. Phase control rectifiers. So usually most of the students might have heard this name rectifier. So if rectifier comes, or if any student take this word or listen this word, what they will do? Immediately they will say diode, or they will think about the diode rectifier. But there are some drawbacks with the diode rectifier. Why? Because if you require a variable speed control or variable output voltage, at that part of time you won't use diode rectifier, because diode rectifier will give a fixed output voltage, but we require, or the application requires, a variable output voltage. So to get the variable output voltage, what we'll do is we'll take the rectifier's concept and we'll use a phase controlling concept by picking the device. Which device will pick? We'll pick the thyristor, that too in the family of thyristor, especially we'll take the SCR into consideration. So by using or by introducing SCR into the rectifier circuit, or by replacing diode with SCR, so you have a variable output voltage you will get by using these circuits. And in these circuits you will have a different kinds of configuration, just like whatever you have studied in your diode rectifiers, like half wave rectifier, full wave rectifier. That too in full wave you will have what type of rectifiers we have: center tapped transformer type, bridge configuration type, all those things will be there. Yes or not? So those things will comes into picture. But along with the resistive load, because in diode rectifiers we have studied, or in analog electronics you have studied about the diode circuits only with the resistive load. But in our electrical engineering, we not only will consider resistive load, we will consider different kinds of loads like inductive load, capacitive load, all those things. So we'll take all the possibilities of your load concepts, into the consideration, then we'll analyze each and every circuit. So that is about your rectifiers topic. This is the rectifiers. The next one is, so what is the purpose of rectifier? Means which converts the AC form of energy into DC form of energy. So what is the next one? The next one, if you take, that is choppers. So what is the purpose of choppers? Means which takes fixed DC form of energy, and which delivers the variable DC, means here you have a fixed DC and here you have a variable DC. So wherever you require a output variable voltage with a fixed DC voltage availability, so there we'll introduce a choppers. In these choppers we'll have different circuits we have, that are buck chopper, buck converter, or buck chopper, boost chopper, buck boost chopper, and voltage commutated chopper. That comes in our commutation circuits. Voltage commutated chopper, current commutated chopper. So these are all comes in this topic, that is called as this module, we call it as a choppers. Okay, the next module what we are going to discuss is inverters. So if you take the inverters, there are third or fourth one, that is inverter. What is the purpose of inverter? Means which converts the DC form of energy into AC form of energy. So here the input is DC, fixed DC, but the output is variable AC. So with the help of inverter circuits, we can vary the output voltage along with the frequency, or you can change the frequency, or you can maintain the same fixed frequency also. That is possible, but mostly we'll use variable voltage and variable frequency technique for the speed control of your induction motors and synchronous motor. There are multiple techniques are there to get the variable voltage and variable current or variable frequency. So this is about the inverters. And the last module of this power electronic circuits is cyclo converters and AC voltage regulators. So we usually call these circuits as AC to AC converters. We usually call these converters as AC to AC converters. We call these circuits as AC to DC converter. We call these converters as DC to DC converters, because here input is DC, output is also DC. Here input is AC, output is DC. Here input is DC, output is AC. That's why we call these circuits as DC to AC converters. Similarly, so here for these cyclo converters and AC voltage regulators, the input is AC and output is also AC. That's why these circuits are also called as AC to AC converters. So this is about the detailed syllabus, individual syllabus analysis of your power electronic circuits. So in these circuits there are different, these cyclo converters are used to change the voltage and to change the frequency also. Here higher frequencies or lower frequencies is possible with the cyclo converters. But if you take the AC voltage controller, the name itself it is specifying AC voltage controller. So voltage can be controlled with this one. So in AC, what are the basic parameters we'll give as an input? Voltage and frequency. Usual supply means will represent with the 50 volt, 230 volts, 50 Hz. So for each and every system will represent the voltage along with the frequency. So in AC voltage regulator, if you take voltage is only the controlling parameter. Here you won't control any frequency. Understood or not? So this is about the simple subject, which one? Syllabus analysis. Now let's move to the first question which is asked in the previous year of your TSPSC exam. Let's move to the questions part. Now, if you take the questions part, first read the question, then what are the concept you might have known about the question. First remember that one or take that one into consideration, then you have to answer the options. So what is the question? First question he has given is an IGBT has, it is not gas, it is has, actually has. There is a mistake in the typing, mistakes will be there in this question paper, in the official question paper itself only. In the official question itself there are some typing mistakes. So an IGBT has. So first you must know about the IGBT. First we must know about the IGBT. So tell me, what is IGBT? How we will consider about the IGBT, and what are the options he has given? He has given options in terms of input impedance and conduction losses. So you need to bring the relation of IGBT relations in terms of input impedance and conduction losses. How you will know about this one? First you need to bring about the basic concept about the IGBT. So what are the basic concept of IGBT? How you will construct the IGBT? IGBT will be constructed, or IGBT is obtained by combining both the BJT plus MOSFET characteristics. How we will construct the IGBT? We will take the BJT, some of the advantages of BJT characteristics and some of the advantages of MOSFET characteristics, and by combining both the advantages, then only we will build the IGBT. So what are the advantages of MOSFET? What are the advantages of MOSFET? As we already know about the MOSFET, metal oxide semiconductor. So as there is a gate terminal, if you take the MOSFET, what are the terminals for MOSFET? Gate, drain, source. So if you take the gate, drain, source into consideration, so at gate terminal you have a open circuit, similar to simple layman language you can say. So there is a open circuit at the gate. So here what are the input impedance of MOSFET you got? You will get a 10,008 or 10 power 8 kilo ohms or mega ohms. So here because of the gate terminal or because of the metal oxide element introduction into the MOSFET, this element exhibits high input impedance. So MOSFET has very high input impedance. But what happens to the advantages of BJT? BJT has an advantage that it is having a low conduction losses. So the losses incurred in the BJT are low. So low losses. So IGBT is built by combining the advantages of both BJT and MOSFET. So what is the advantages of MOSFET? It is high input impedance. So first let me take the options of high input impedance. So I can eliminate these two options by taking this high input impedance as a consideration. Then what is the low conduction losses? We have high input impedance and low conduction losses. So option 1 is the right answer. So in this way you need to remember or you need to memorize the concepts which are asked by the examiner. Okay, now let's move to the second question. So if you take the second question into consideration, so what is the second question he has given? Choose the correct statement from the following. If you read the question options, if THD increases, input power factor increases. If THD increases, input power factor decreases. So displacement factor increases, input power factor decreases. Displacement factor increases or decreases, input power factor remains constant. So this is the question. Now first you need to bring the relation, because two options having a relation between THD and input power factor, and another two options are how they are the relation between, it specifies the relation between input power factor and displacement factor. Now first write the relevant equations, mathematical equations, whatever you know about these four terms. So now First, let us write the input power factor equation. So what is input power factor equation? It is the ratio of fundamental source current RMS fundamental source current to the RMS source current value multiplied by cosine of the angular difference between your voltage and current. So this is the input power factor definition, whatever we know. Now from this one, as we already know about the displacement factor and current distortion factor, so we call this term as displacement factor, which will be called as DPF, displacement factor DPF. And the ratio of your fundamental source RMS current to the RMS current, we call this term as which one? Distortion factor or current distortion factor. So we call this as a current distortion factor and we call this as a displacement factor. Now as two options like third option and fourth option, if you remember, so there is a displacement factor relation between input power factor. Now if you see, if there is a change in the displacement factor, will the IPF or input power factor will remain constant? No. If this increases, this is also increases. If this decreases, this is also decreases. So option 4 can be eliminated directly by using this equation. Yes or not? Now if displacement factor increases, input power factor decreases, he has mentioned. So if this increases, what happens to the input power factor? This is also increases. So option 3 also eliminated. Yes or not? So now what we have to do, we need to bring the relation, because we removed the two options, we have only two options. So even if you don't know the mathematical relation between these two also, then you have a 50% probability to get the mark. Yes or not? So if previously 4 options are there, you have only 25% probability, but now your probability is increased by using the known equations. Now what we'll do is, let us write the relation between THD and which one? Input power factor. Now how we'll write the THD relation between THD and input power factor? What is THD? Square root of VOR square, yes or not? Which one? Or you can write IOR square also, no problem. IOR square minus IO square divided by IO square. So this is the THD relation. Yes or not? So if you take this relation into consideration, and if you remodify this one, so finally what we'll get is THD is equal to square root of, so if I divide this denominator term individually to the numerator, what will get? IOR square by I naught square minus 1. So if you take the current distortion factor, ISR I naught both will be same if the circuit is having a constant current. If the circuit is carrying a constant current, both IS and I naught will be same. So we can rewrite this equation like this again, because we know the relation between your which one? Current distortion factor. We know the relation for current distortion factor, that is IS1 or IOR, with the relation between IOR to IS. Yes or not? So we can rewrite like this: 1 by I naught square by IOR square minus 1. So this can be rewritten as current distortion factor also. We can rewrite this one as current distortion factor. So if you know the current distortion factor relation in terms of IPF, then you can get the relation between THD and IPF. Now let's take a new slide. Okay. So if you take this one, so what the relation we got? THD is equal to square root of 1 by current distortion factor square minus 1. So we know that input power factor is equal to how much? current distortion factor multiplied by displacement factor. So from this one, what is current distortion factor? Which is equal to input power factor divided with displacement factor. Now let's substitute current distortion factor here. So which is equal to square root of 1 by IPF by which one? DPF whole square minus 1. So if you take this relation into consideration, what is happening? If IPF increases, what is happening? This denominator part will increase. If this part increases, this entire part will decrease. So if this decreases, your THD is decreasing. So I can say that THD is nearly or almost inversely proportional to IPF. We can say, not exactly, nearly we can say. So because of this relation, or you can take square also, no problem. So THD is inversely proportional to IPF. So from these options, what are the options which will suit for this question? If THD increases, input power factor decreases. This is the right answer. This is the right answer. Understood or not? So in this way we need to solve. See, here I took the much amount of time because to explain in a easier fashion. But if you want to have a, if you know these concepts very well, you can solve this question in a within 30 to 40 seconds itself. Okay, now let's move to the next question. What is the next question he has given? Which of the following devices has the lowest maximum switching frequency? So which will have a lowest maximum frequency, switching frequency? As we already know about the MOSFET is used for very high switching frequencies. This will be used for very high switching frequencies. After this one, which one is the next higher switching frequency device is your Igbt, because Igbt is also a combination of both MOSFET and BJT. So BJT advantage is it is used for higher switching frequencies. That advantages also will take into consideration while building the Igbt. So the next one is Igbt. What about the next one? GTO, gate turn off thyristor. So this is also having a next higher value. So the least one will be, means this is very high, this is high, this is medium, and this is the least switching frequency. So which is the correct answer for this question? SCR is having the least or lowest maximum switching frequency. Understood or not? Now let's move to the next question. What is the next question he has given is a single phase full converter. So here he has mentioned the converter type with load also. Single phase full converter with RL load. So as we already have a single phase full converter with RL load, so first let us draw the circuit. So as it is mentioned in the full converter, so we need to take the SCR converter. Full converter means it is bridge converters. Yes or not? So bridge converters means how the supply, this is the supply. So this is your supply, this is your supply, and here what type of load is there? RL load. So this is the circuit. So here we have a output voltage, here we have a output current. Now if we take this circuit into consideration, assume the direct thyristors T1, T2 here, T3 and T4 here. So if you take this one, RL load means we can say, because nothing is mentioned about the load, I can say that this is a continuous conduction of current load or a constant current load. So as nothing is mentioned about the continuity or discontinuity, we need to take, or we can take for easy answering purpose, a constant current load. So this can be replaced like this. So if this is a constant current load, so what is the question he has asked? It is these devices are triggered at 30 degrees. If you take the supply voltage, sinusoidal supply voltage, omega t is the x-axis, this is the sinusoidal voltage V in. So how the sinusoidal voltage looks like? This is the sinusoidal voltage. Yes or not? So where the devices are triggered? The devices are triggered at 30 degrees like this. So at this 30 degrees devices are triggered. So at 30 degrees devices are triggered. How the output voltage? Output voltage will follow, because T1 and T2 are triggered simultaneously and T3 and T4 are triggered simultaneously, and these T1, T2 and T3, T4 both these pair of devices will operate in complementary fashion. When these two are in turned on, these two will be in off state. When these two are in on state, these two will be in off state. So from 30 degrees, which device will start conducting? Your devices T1, T2 starts conducting. So your output voltage. So when T1, T2 is conducting, let me take this output voltage as A, B. When T1, T2 conducts, A is connected to positive, B is connected to negative. So your output voltage is, this is VAB. VAB. So your output follows the VAB like this. And at this point, what is happening? Assume, at this point, assume from here output voltage follows the input voltage. At this point, your devices try to turn off because of the application of zero voltage across the devices, but because of the load current, constant current, so this load or this DC current load or this continuous conduction of load will force the devices T1, T2 to stay in the on state until the next pair of devices are turned on. So these will be turned on, or T3 and T4 are turned on at this place, that is 30 degree watt, this is 210 degree. At 210 degree T3, T4 are turned on. So till T210 the devices T1, T2 will be in conduction. That's why you will get output voltage like this. So this is the output voltage, and this is the next pair of output voltage. So this is the conduction of T1 and T2. So from where to where T1 and T2 are conducting? From 30 degrees to 210 degrees. Means what is the total conduction period of each device? Each device is conducting from how much angle? 210 to 30 to 210, that is 210 minus 30 degrees, it is 180 degrees. So each device conducts for how much amount of angle? 180 degrees. This is how you need to solve the question. Now let's move the let's move to the next question. What is the next question he has given? In which of the following both frequency and voltage can be controlled? In which of the following both voltage and frequency are controllable? Now this question you can solve in 10 seconds if you remember the basic idea about all the circuits. So what is the question he has asked? Frequency and voltage both are controlled. So if you take the names, inverter, AC voltage controller, cyclo converter, these are the four names we have. Yes or not? So if you take the AC voltage controller, is it controls the frequency and output voltage? AC voltage controller, it controls both voltage and frequency, or it will control only voltage? See, AC voltage controller only controls output voltage, it won't control the output frequency. So you can eliminate the option which has AC voltage controller in that. So first option you can eliminate directly. I am solving this question using option elimination. So second option is also having the AC voltage controller. In third you don't have a AC voltage controller, but if in fourth again AC voltage controller is available, so I can eliminate. So the final answer is which one? Third option is the right answer. Yes or not? So in this way you need to solve the problems based on the question. Based on the question you can solve the question. Okay, so options also you can use elimination, option elimination technique. Let's move to the next question. What is the next question he has given? If you take the next question into consideration, a circulating current mode dual converter has the following properties. See, here the question itself, it is mentioned as circulating current mode dual converter. If you take the dual converter, what is the dual converter operation? How it will operate means, you will have two converters, one converter on left side, converter 1, another converter on right side, like this. So these two converters are connected in fashion like this across a load like this. But what is the additional thing here he has given is, What is the additional thing here he has given? He mentioned as which one? Circulating current mode of operation. And so in circulating current mode of operation, we'll introduce a inductor into the circuit. So this is the circulating current mode of dual converter. So dual converter, dual, it means two converters connected in back-to-back fashion. So two full converters are connected in back-to-back fashion. So to obtain this one, and here usually we'll use motoring load to get the 4-quadrant operation. Now what is the question and what are the options he has given? He has given options in terms of two terms. One is size, another one is efficiency. One is size, another one is efficiency. So if you take the basic dual converter, here we don't have a inductor, but to avoid the circulating current, what they have done is they have introduced, or to limit the circulating current, introduced a series inductor into the circuit. So once there is an inductor, or inductor means it is a coil. Once coil is introduced, what is happening? Size becomes bulky. Yes or not? Coil means you need to take the copper wires in the, you have to wound on some particular core, iron core or air core, anything. So the size of the system becomes increases because of the presence of your inductor. And apart from this one, what are the other one will get? So because of the presence of inductor, this coil consists of some resistance. So two coils we have. Two coils exhibit some resistance. Those resistance carries current during the circulation of current. During the circulation, these two coils again carries the current, which incurs some amount of losses in the system. So because of the introduction of circulating, to limit the circulating current, what we have done? We introduced the inductors. Because of the inductors introduction, the extra losses are incurring in the circuit. Because of that extra losses, because losses are increased, what happens to the output? Output will decrease. So if output decreases, what happens to the efficiency? Efficiency will fall down. Yes or not? So which options are correct? Efficiency will be low and size will be high. So which options are more? One, size is more and efficiency is low. Size is more and efficiency is low. So this is about the question. Now let's move to the next question. What is the next question he has given is, the firing angle of single phase AC voltage controller is 0. So single phase AC voltage controller he has given, and its firing angle he has mentioned as 0, assuming resistive load, and the input current wave shape. How the input current wave shape looks like? So if you take the AC current voltage regulator, so thus input is AC, so here input is AC we need to consider, and output is also you will get a AC, and what type of load he has mentioned? A resistive load. In between this one, a device, which device we usually use is a triac device. We'll use a back-to-back connection of your SCRs elements we usually use in AC voltage controller. So let us take this T1, this is T2. Now, what is the question he has asked? This is the basic circuit of your AC voltage controller with a resistive load. So you can replace with the generalized load, but here especially mentioned as resistive, just take resistive only. Now, input wave current wave shape. So this is the source current, this is the source current. Now, see here, if T1 is turned on, how the source current and load current? Source current and load current both are same. Source current is equal to load current if T1 is turned on. Yes or not? If T2 is turned on, how the source current and load current? This is the source current direction, and this is the source current direction. And what is the load current direction? Actually, the current is flowing through the SCR in this direction. The current is flowing through SCR in this direction. I'll represent with the SCR current direction. So this is the current flowing through the SCR in this direction. But this is the load current, I can say. Load current is flowing in this direction, but how the source current direction? It is opposite to the load current. So I can say that the source current is equal to minus I0. Minus I0. Yes or not? So what type of supply is available across the resistor? It is sinusoidal voltage, right? Input is sinusoidal. So sinusoidal voltage is applied across the resistor means what type of current you will get? Sinusoidal current. Yes or not? Yes or not? So because of this one, source current is also a sinusoidal in nature. Source current is also a sinusoidal nature. So its value is AC sine wave. AC sine wave. Understood or not? So this is how you need to solve the questions. Let's move to the next question. The next question is, output frequency of a single phase cyclo converter is found to be 12 Hz. Then what is the input frequency? See, in the cyclo converters, whatever the output frequency is equal to integral multiples of your input frequency. See, always your input frequency is equal to how much you will get? N times of your output frequency. N times of your output frequency. So output frequency, we know we need to multiply with some numbers. Which number is satisfying the multiples of output frequency? You need to pick that answer. So 12 is the output frequency. So 50 is multiple of 20, 12? No. 60 is multiple of 12, right? 40 is not a multiple, 30 is also not a multiple. So answer is 60 Hz. 60 Hz. So let's move to the next question. What is the next question he has given? If the duty cycle of a chopper is alpha, what is the ripple factor he has given? So what is the ripple factor? He is asking if you know the duty cycle as alpha. So to answer this one, first you need to know about the chopper output voltage in terms of average values and in terms of RMS values. So if you take the average values, let me write directly the equations. There we will discuss, wherever we have a discussion about the chopper, there we will derive this one. Okay, so root of alpha into VDC. So what is ripple factor actually? Voltage ripple factor, if you take, this is equal to square root of VOR square minus V0 square divided by V0 square. So what is VOR? Actually it is root alpha into VDC. Square means alpha into VDC square minus alpha square into VDC by alpha square into VDC. Yes or not? So take alpha in the numerator, one alpha in the denominator cancels each other. So the final voltage ripple factor, what is the equation you will get? Square root of 1 minus alpha into VDC square divided by alpha into VDC square. So VDC square gets cancelled. So finally the voltage ripple factor is 1 minus alpha by alpha. So option 1 is the right answer. So in this way you need to solve the questions based on the given data. Now let's move to the next question. What is the next question he has given? The next question is, this is the next question. The converters which operate only in two quadrants, which converters are operating in two quadrants? So in the phase control rectifiers discussion, will prove that semi-converter or half converter or semi-converter operates only in which one? Only in first quadrant. In the remaining three quadrants you won't get any operation of semi-converter because of the freewheeling action obtained by the devices. So whatever the option consists of semi-converter, you can eliminate those options directly. So semi-converter, here semi-converter is there, here semi-converter is there, here semi-converter is there. So all the semi-converter options you can eliminate. The one and only leftover option is which one? Half wave control rectifier. Half wave and full wave converters both have which one? Two quadrant operation. So this is how you need to solve the problems in different subjects. Let us discuss different kinds of techniques in future also. Okay, so what we'll do is we'll wind up this session now and we'll discuss few more questions. This question series will keep on coming on this TSPSC. Okay, so let's discuss another paper questions about the power electronics circuit first, then later we'll discuss the drives questions also. Okay, so I hope you enjoyed this session and you understood this session. Thank you, all the best.